The topic of this lecture is Important Theorem Part 2 of Improper Integral. We'll cover these points in this lecture: theorem, useful comparison integral, theorem, mu test, a practical test, an example based on comparison test. So let us see this theorem. The integral a to b dx upon x minus a to the power mu is convergent if and only if mu is less than 1. This we have to prove. So let us see the proof. The integral a to b dx upon x minus a to the power mu is proper if mu is less than equal to 0, because in this case this expression goes up in numerator and there is a no problem. Now if mu is greater than 0, then let us suppose fx is equal to 1 upon x minus a to the power mu, where x lies between a and b, not including a but including b. In this case, the only point of infinite discontinuity of f is x is equal to a, and it is integrable on a plus epsilon to b for epsilon lies between this interval, and clearly fx is greater than 0 for all x lies between open interval a closed interval b. Now let us define phi epsilon by this integration a plus epsilon to b dx upon x minus a to the power mu. Then recall, if this expression goes to 0 as limit epsilon tends to 0, then this improper integral will be convergent, otherwise it will be divergent. So let us take the case, first of all, if mu is not equal to 1, then when we evaluate this, we get this expression phi epsilon is equal to 1 upon 1 minus mu b minus a to the power 1 minus mu minus epsilon to the power 1 minus mu. This expression we get. Now let us take case 1 when 0 is less than mu less than 1, that is mu lies between 0 and 1. So 1 minus epsilon will be greater than 0 in this case, and when we take the limit from this expression we get 1 upon 1 minus mu into b minus a to the power 1 minus mu, and this goes to 0. So in this case we are getting finite limit. So if 0 less than mu less than 1, then this improper integral is convergent. Now let us take case when mu is greater than 1. In this case mu minus 1 is greater than 0. So again from this expression when we take the limit as epsilon tends to 0, we get the infinite. So clearly when mu is greater than 1, this improper integral is divergent. Now let us take the third case when mu is equal to 1, then phi epsilon becomes this expression, and when we evaluate this integral, we get log x minus a to, from a plus b to a plus epsilon to b, and we get this expression, and when we take limit epsilon tends to 0, we get infinite. So when mu is equal to 1, the improper integral is divergent. So since limit epsilon tends to 0, phi epsilon exists finitely when 0 less than mu less than 1, and this limit becomes infinite when mu is greater than equal to 1, the improper integral, this integral is convergent if and only if 0 is less than mu less than 1. And if when mu is less than equal to 0, that we have seen the case, there is no problem. So finally, thus the integral a to b dx upon x minus a to the power mu is convergent if and only if mu is less than 1. So this was the proof of this theorem. Now let us see one more theorem. Mu test, a practical test. Here again, what are the suppositions? A is the only point of infinite discontinuity of function f, which is integrable on this interval, open interval a to b. B is closed when epsilon for every epsilon satisfy this inequality and fx is greater than 0. This is our assumption. And limit x tends to a plus fx into x minus a to the power mu is equal to L. This is our assumption. Now if this L is a non-zero finite number, then the integral a to b fx dx is convergent if and only if mu is less than 1. So from this to this, all these are our assumptions, and if this assumptions holds, then the improper integral this is convergent when mu is less than 1. Okay, let us see the proof. Since fx into x minus a to the power mu is greater than 0, because fx is greater than 0 and x minus a to the power mu is also greater than 0, or all x lies between open interval a closed interval b, so we can select a positive delta greater than 0 such that L minus delta is greater than 0. Because in this case, L is greater than 0, so we can select delta such that L minus delta is greater than 0. And as the limit x tends to a, fx x minus a to the power mu is L, so we can find a point C belongs to open interval a close interval b such that this expression holds, that is L minus delta is less than fx into x minus a to the power mu is less than L plus delta for all x lies between open interval a to close interval c. Or if we divide all expression by x minus a to the power mu, we get this expression. Now let us take different cases. If mu is less than 1, the integral 1 upon x minus a to the power mu dx is convergent. That we have seen in last year. And this L minus epsilon creates no problem because it is greater than 0, a constant. So it follows the from right hand inequality, this is right hand inequality, that integration a to c fx dx is convergent. So this will also implies that integration a to b fx dx is convergent. Now if mu is less than equal to 1, the integral a to c 1 upon x minus a to the power mu x is divergent. That we also seen in the last theorem. And as L minus delta is greater than 0, it follows from the left hand inequality. What is left hand inequality? This was the left hand inequality. L minus delta into x minus a to the power mu is less than fx. This follows from this inequality that the integration a to c fx dx is divergent, and this implies that a to b fx dx is also divergent. Therefore, a to cx fx dx is convergent if and only if mu is less than 1. So, fx dx, a to b fx dx is convergent if and only if the case when mu is less than 1. So remark, if limit x tends to b plus fx into x minus a b minus x to the power mu is equal to L, where L is non-zero finite number, then the integral a to b fx dx is convergent if and only if mu is less than 1. That is, if b is the point of infinite discontinuity, so this limit can be used in this case. Now let us see one example based on comparison test. Examine the convergence of the integral 0 to 1 x to the power p minus 1 upon 1 plus x dx. Let us see the solution. The integral is proper when p minus 1 is greater than 0. So between 0 and 1, this does not create any problem in the sense that it is integrable. Now if p is less than 1, p is less than 1, then 0 is the only point of infinite discontinuity of the integral. Because when p is less than 1, this expression goes down and 0 becomes a point of infinite discontinuity. Now let us suppose fx is equal to x to the power p minus 1, x to the power p minus 1 upon 1 plus x. X lies between 0 and 1, and let us take gx is equal to x to the power p minus 1. That is the new function. We are taking gx. Then clearly fx is greater than 0 and gx is greater than 0 in this interval. And taking limit x tends to a 0 plus fx by gx, it is equal to 1. because fx is this, gx is this. When you calculate and take the limit x tends to 0, you get 1, which is a non-zero finite number. Therefore, the integral 0 to 1 fx dx and 0 to 1 gx dx converges or diverges together. Now the integral 0 to 1 gx dx, that is 0 to 1 upon x to the power 1 minus p. From this we have written in this fashion, it is convergent if and only if 1 minus p is less than 1. Here 1 minus p is, as in the previous theorem, this is the value of mu. So it is less than 1. So this is if and only if p is greater than 0. From this we can get easily p is greater than 0. Therefore, the integral 0 to 1 x to the power p minus 1 upon 1 plus x dx is convergent if and only if p is greater than 0. So by this way, this is easily solved. Thank you very much. You can find the link of this lecture as a PDF in the comment box. Thank you.